those words, you think what? Slope. It's a slope calculation, change in y over change in x. And you drew in that secant line, and that secant line had the slope that you calculated, between 5 and negative 5. And then I said, is there another point on your function where the tangent line would be parallel to that secant line? And all of you were able to find at least one point where the tangent line was parallel to the secant line, correct? Okay. Did anyone find more than one?
Yeah.
Yep. Matt had them all over his paper. They were all over the place. All right, so what happened is we found at least one point where the slope of the tangent line is equal to the slope of the secant line. Well, what's another word for the slope of the tangent line? Instantaneous rate of change. Good. And what else? The derivative. All right. So on the back of your investigation, flip it over. It says, so from this investigation we have found that if we have a continuous differentiable function on an interval on a closed interval from A to B, there will exist at least one point where the words that we want to put in there are the average rate of change is equal to the instantaneous rate of change. Average rate of change equals instantaneous rate of change. And the notation underneath, where you have written average rate of change, what I want you to write is this: f of b minus f of a over b minus a. That's just a slope calculation on an interval from A to B. So this is what you put in under average rate of change. And this is what you put in under instantaneous rate of change. Okay? So what you have just graphically investigated is called the mean value theorem. And you will be using it a great deal. It becomes very useful in a lot of different situations. But the first thing I want you to remember about this is there are two conditions that must be met. And the conditions are that the function must be continuous at every point in the closed interval and differentiable at every point in the open interval. So continuous on the closed, that means we need to have closed circles at the end of our interval. And differentiable everywhere in between, which means what? What can there not be? Cannot be cups, corners oscillating. It's hard to get that out. All right. So you must, to apply the mean value theorem, you must always check these two conditions first. So when you have a mean value theorem problem, I should see 1, continuous, check mark. 2, differentiable, check mark. Then move on. Okay? All right. So the general picture that you will see most often with the explanation of mean value theorem is something like this. So here's my function on the interval from A to B. Here's my slope of the secant line, or I should say that is my secant line, right here, and here's the slope of the secant line. And there will exist at least one point C, that is between A and B, such that the slope of the tangent line at C will equal the slope of the secant line. Any questions on the graphical background here? Stay with me, Matt. Okay? All right. Let's try a few problems. Oh, no, sorry. I left this on purpose. So a few of you had chosen functions that looked something like this. Where your f of 5 and your f of negative 5 had the same y value, right? Fred, you had one. Somebody else had them. Yep, good. All right. This is a special case of the mean value theorem, so this should go into your notes. Special case of mean value theorem called Rolle's theorem. And this says, if we have a function that is continuous on the closed interval from A to B and is differentiable on the open interval from A to B, and one more condition, f of B equals f of A. So we add one more condition that f of B has to equal f of A, then what do you think the conclusion is of this theorem? What must be true? There must exist, very nice, exist at least one point where f prime of C equals 0. Because if it is continuous and differentiable, it means it is a smooth curve, and if I start at one point and end at the same point, then at some point it has to smoothly turn around and come back to that same beginning point, same beginning y value. So there must be a point where the derivative would equal 0. Now, if you didn't specifically call this Rolle's theorem and just use mean value theorem on this type of problem, you would come up with a derivative equal to 0. So it's not something you have to specifically separate from mean value theorem, but it is considered a special case of it. Yeah?
Isn't it just like a specific application of the mean value theorem?
It is. Yep.
Okay.
Quite often, though, you will see reference to Rolle's theorem instead of mean value theorem. So it's just nice to know their link. Okay? All right, so let's go see how we use mean value theorem. All right, show that the function f of x equals x squared satisfies the hypotheses of the mean value theorem, those are the conditions, on the interval from 0 to 2, then find the solution C. So we're looking for the point where the derivative equals the average rate of change to the equation. All right, well, we need to first check our conditions, our hypotheses. Is x squared continuous on the closed interval 0 to 2? Oh, closed. Yes or no? Yes. Continuous everywhere, so it is continuous on that interval. Second, is it differentiable on the open interval? Well, the derivative is 2x, and is that differentiable? Is f of x differentiable everywhere between 0 and 2? Does 2x exist? Okay, so when you check this, to be continuous on the closed interval means that these points at the end have to be filled in. No holes. And to be continuous on the, differentiable on the open, it doesn't matter if we're differentiable at those endpoints, but it needs to be differentiable everywhere in between. Okay. Those are the only two conditions that have to be met. All right, so we are differentiable on the open interval from 0 to 2, yes. So now what we need to do is find the point C where the average rate of change equals the instantaneous rate of change. So we will do f of b, which will be f of 2 minus f of 0 over 2 minus 0 equals f prime of c. So what is f prime? 2x. Well, f prime of c then would be 2c. And we're trying to solve for c. All right, well, what is f of 2? 4 minus, louder, 0, over 2. So on the right side we have 2, and on the left side we have 2c. Solve for your c. So at c equals 1, that is where the slope of the secant line would be equal to the slope of the tangent line. Yes?
Why did you put TC?
Because the mean value theorem says that there exists some point C where the derivative equals the average rate of change. So we're evaluating our derivative at C and solving for C. Okay? All right. So at this point, the slope of the tangent line equals the slope of the secant line. Yeah. Oh, no, Zach, you're not waving to me. No question for me, just waving? Okay. All right. Try this one, please. Explain why each of the following functions fails to satisfy the conditions of the mean value theorem on the interval from -1 to 1. First thing I want to point out, we talked about this once before. What is another way to write the square root of x squared? That is the same as what? Absolute value of x. This is the definition, thank you, of the absolute value of x. So why would this one, why would the mean value theorem conditions fail for this function? Got a point, got a sharp turn, got a cusp, whatever you want to call it. We have a cusp or a corner at what? X equals what? 0. So it is not differentiable. All right, how about this one? So first we're going to check to see if it's continuous. It is not. If we plug 1 in on the left branch, we get 4, correct?
Yes.
Okay, and on the right branch, we get what? Good. Not continuous. Okay. All right. I can't do that. So the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. So it is not a continuous function. What must be true for a function to be continuous?
Limit from the left equals limit from the right.
That's one thing. So the limit must exist.
Value of the limit has to equal the value of the function.
Yes, perfect. The limit must exist, the function must
Right.
exist, and they must be equal. Very nice. All right. Can I move on? Am I good to move on?
Yes.
Okay, I'm moving on. All right. Let f of x be the square root of 1 minus x squared, and a is the point -1 f of -1, b is the point 1 f of 1. Find the tangent to f in the interval from -1 to 1 that is parallel to the secant of AB. You all try this right now at your desk, please. All right, let's take a look. So find a tangent line. So we're going to be plugging into, y minus blank equals m times x minus blank. In the end, that's what we're looking for, an equation of a tangent line. All right, find a tangent to f in the interval from -1 to 1 such that that is parallel to the secant AB. All right, well, how do we find this? Let me start. If it needs to be parallel to secant AB, then what has to be true? slope has to be the same. So to be parallel, the tangent must have the same slope as the secant. Okay, so what does that imply? If our tangent has the same slope as the secant, it's leading us to this mean value theorem, correct? Because that's what the mean value theorem says. So let's check the conditions of the mean value theorem to see if this is possible. So is f of x continuous on the closed interval? All right, well, what is this thing? Does anybody know what that looks like? That's semicircle, right? Half a circle? Looks like that. So is that continuous on the interval from -1 to 1? Indeed. Check. All right, the second thing we have to check is if it's differentiable on the open interval. Well, to figure that out, we need to find the derivative. Okay, so what is the derivative f prime of x? Is what? 1/2. Good. To the? Good. Times? Times -2x. So if we rearrange this a little bit, it looks like -x over the square root of 1 minus x squared. So that is the derivative function. Is that defined everywhere between -1 and 1? Where is it not defined? It is not defined at x equals positive or -1. Well, is that okay? Because we're differentiable on the open interval in between them, so we're okay. All right, so that means that the mean value theorem applies. And it means that -c over the square root of 1 minus c squared will equal f of 1 minus f of -1 over 1 minus -1. So what do I get on the right side? F of 1 is 0. F of -1, also 0, over 2.
Oh, you're right.
Am I okay?
No, yes.
I think I'm all right.
I did it the other way.
Okay, yes. All right, so we get -c over the square root of 1 minus c squared equals 0. How do I solve that equation? Donna. Basically, yep, we clear the fraction and the bottom would basically go away, so we get -c equals 0. So this happens at c equals 0. All right, so that means that is my x value, correct, for my tangent line? All right, and if x equals 0, what does y equal, or f of 0 equal? What is it equal to 1? All right, so now we can write our equation, and that is y minus 1 equals blank times x minus 0. So we have found our x and our y. How do I find my slope? Nathan, what do I do for that?
Is it the secant line?
It is parallel to the secant line, right?
So it is 0.
It is 0. We already found the slope of the secant line up here. The other thing you could do is plug 0 into your derivative. You could do that. So we end up with the equation y equals what? 1. Does that make sense for our sketch? Indeed it does. And we have done a problem that actually deals with Rolle's theorem, where f of b equals f of a, and we're guaranteed to have an x value in the interval where the derivative equals 0. All right, sorry, we got to do a couple other little things. Okay, just addressing these quickly. Determining where graphs rise and fall. So where is the function f of x equals x cubed minus 4x increasing, and where is it decreasing? So we're not going to do this entire problem, but we're going to take our notes on how to approach it. So if I want to know where a function is increasing, what am I looking at? Where the derivative is what? Greater than 0. To see when we're increasing. And then, where the derivative is less than 0, to see where we're decreasing. So on these, we would have 3x squared minus 4 greater than 0, solve for that. And 3x squared minus 4 less than 0, find where that happens. Okay? I will say, be careful when dealing with inequalities and parabolas. Think graphically. Okay. All right, let me see if there's anything else I want to get to before you go. Take a look at these two pieces of information. Functions with the same derivative differing by a constant. So, if f prime of x and g prime of x are equal, so let's say f prime of x is 2x, and g prime of x is 2x, then there is a constant c such that f of x equals g of x plus c. Well, what did I start with to get a derivative of 2x? I started with x squared, so f of x could be x squared. And give me an example of what g of x could be to also get 2x as my derivative.
Something different.
Yes, yes. Or something very similar, but different by a constant. X squared plus 4 would do it. So just that simple difference of a constant would lead us to getting the same derivative for f and g. All right, and what we just did, by thinking about what did I start with, if I got 2x as my derivative, is called finding the antiderivative, notated with a capital F. So if f of x is my function, f of x is my function. Hold it, this way. F prime is my derivative. And capital F of x is my antiderivative. I'll finish up the last example on the video for tonight. Your homework is on the assignment sheet. Sorry to go on the end. Have a good day. Okay, for our last example, we have example 8 using this idea of an antiderivative. So we're asked to find the velocity and position functions of a body falling freely from a height of 0 meters under each of the following set of conditions. In part A, they tell us the acceleration is 9.8 meters per second squared, and the body falls from rest, which tells me that its initial velocity is 0, and its acceleration function is 9.8 meters per second squared. Now, we have dealt with position, velocity, and acceleration problems already, and we have, when we did these, we saw that we would take the derivative of position to get velocity and take the derivative of velocity to get acceleration. Well, this time we're working backwards from acceleration. So, when you work backwards from acceleration to velocity and then to position, you take the antiderivative. And when you take an antiderivative, you must remember as we showed on the previous slide, that our original functions can differ by a constant. So when we take the antiderivative, we follow it with a plus c, which could be any constant. So we need to remember to use that when we do the anti-differentiation process. So now we ask ourselves, if my acceleration was 9.8, then what was the velocity that gave me that acceleration? Well, we took the derivative of something to get 9.8. So it makes sense that what we started with was 9.8t. But we need to remember it can be plus any constant. So our velocity function is 9.8t plus c. And if you take the derivative of that, you get 9.8 for the acceleration. So that works. But now we need to solve for that constant. So we use what is called an initial condition, which in our case was that the body falls initially from rest, so the initial velocity was 0. So at time 0, the velocity is 0. So that's what we're doing here. We're putting 0 in for velocity and 0 for time and solving for c. In this case, c ends up being 0, so our velocity function was 9.8t. Well, the problem asks us for a position function. So we have to go through that process one more time. So now I have to think about, if I ended up with 9.8t as my derivative, what did I start with? Well, we know that if we take the derivative of t squared, a quadratic, it gives us 2t. But we don't want 2t, we just want t. So what we must have started with would be 9.8 times t squared over 2. When I take the derivative of that, the 2 comes down in front, so we have a 9.8 times 2 times t over 2. The 2's cancel, and we are left with 9.8t. So I must have started with 9.8 t squared over 2 plus some other constant. This time I've named it c1. And that is my general solution to the position function. And again, it tells us that the body is falling freely from a height of 0, so our initial height is 0, so s of 0 equals 0. And again, we need to solve for the constant. So we put 0 in for the position, we put 0 in for the time, and we solve for c1. And in this case, again, our constant comes out to be 0. So my position function is 9.8 t squared over 2, which is 4.9 t squared. We have one last example, part B of this problem, which says the acceleration again is 9.8 meters per second squared, and the body is propelled downward with an initial velocity of 1 meter per second. So that's what has changed. My initial condition is not 0 this time, but it is 1. So again, I say, what did I start with if when I took the derivative I ended up with 9.8? So I must have started with 9.8t plus some constant. Now when I solve for the constant, I'll put 1 in for velocity and 0 in for time and solve for c. And this time our constant comes out to be 1. So our velocity function is 9.8t plus 1. We aren't looking for velocity, we're actually looking for position. So we need to go through that anti-differentiation process one more time, and again I'm going to step through it. So if I took a derivative of something, and the answer came out to be 9.8t, well then it had a constant out in front, and what did I start with to get t as my derivative? Well, we know when we take the derivative of t squared, the derivative of t squared is 2t. But we did not end up with 2t, we ended up with 9.8 as a constant out in front times t. So I must have something that cancels out that 2. So I must have started with 9.8 t squared over 2. So let me move this down a little bit. If we look at the derivative with respect to time of t squared over 2, we get 2 times t over 2. The 2's cancel, and we are left with t. So, if when I took the derivative I ended up with 9.8t, and I must have started with 9.8 times t squared over 2. So that's what we get here when we take the antiderivative of 9.8t. We get 9.8t squared over 2. Plus, what did I start with to get a derivative of 1? Well, I must have started with t, because the derivative of t is 1. So now I have 9.8 t squared over 2 plus t, again plus some other constant. I'm labeling C1. We're still falling from a height of 0, so at time 0 the height is 0. So I put 0 in for the height, 0 for the time, and I solve for C1. Once again, my constant comes out to be 0. So my position function in this case will be 9.8 t squared plus t.